Hello, Professor. Today we're going to be studying the behavior of airflow over airfoil. So to begin with, this is the website we're using, airfoiltools.com, and this is the website we're using to design the airfoil and get it for our console software. So we're going to be using the NACA0015 shape, and these are the software. This is the console software. And in this first step, we're opening the model wizard, and then we're selecting 2D. Then we're going for a single phase laminar. So yeah, fluid flows, we go for single phase. And then from here, we click add, and then we study. So now we're going to be studying steady state flow, which is very important. And then we don't go for we go for a stationary one, and then we press done. So now we wait for the software to load. All right, it's going to take a while. Perfect, here it is. So we're going to be importing the airfoil file into the software, for which we'll go to geometry, then we go to polygon, and then we make sure our data source. So we find the file, and then we look for our data. There it is. And then we're going to be drawing a rectangle that represents the flow of air around the airfoil. So we're just setting up subdimension. So we go to polygon. I think we're supposed to look for rectangle. Yeah, rectangle, there it is. And then we make the width and height the same for now, because we're just measuring. So we choose this on our own. Let's make it 3 and 3. Yeah, that becomes a square, but yeah. And then we're going to base it on the center of the airfoil. So we put some random central coordinates, so 1 3 2, and we make this 0. Okay. And now the rectangle should come around as you can see, it's come around the airfoil. So this is going to be acting as our air area. All right, so now we're going to be rotating the airfoil a bit by an angle to be studying it. So we're going to be choosing the airfoil to be rotated, and let's make the angle -5 in our case. So we select the object. Okay, yeah, it's selected. We go to the angle, let's click -5. And then from here we can go to booleans and partitions to separate the airflow from the airfoil. So we select the entire area, difference, yeah, we select the entire area, and then we build selected, and then we select the airfoil. All right, and then we go to select the material, okay, build selected is coming. All right, now let's look at the material. Which we need to look for is air. So we need to go to the library now. Let's click materials.
Once you go to browse, we go to built-in air and we select air for our material. Next step is the mesh. Now we have to make our mesh. We go for a fine setting. In this case, we go for fine setting because, as you can see in the graph, at roughly 6000 it starts converging, and this mesh won't take much time to simulate. This converges the fastest. This is what the mesh looks like once it's done. The next step is to set the boundary conditions. First, at the inlet, we set a velocity of 0.2 meters per second. And then we need to set the boundary conditions at the outlet. The pressure is at 0. Now we have to conduct a study for the velocity and pressure, which will give us a diagram that we will see shortly. Which will give us the red part over here. The red part represents the fastest areas of the velocity, and the blue part is the minimum velocity, which can be 0 at some parts. As you will zoom in over here, we will see that the blue parts at the edges represent the no-slip boundary condition, where the velocity indeed is 0 as part of the no-slip boundary conditions. As you can see, here is the pressure behavior for the airfoil. The red color shows minimum and the blue color shows maximum pressure. At this point here, for example, is the airfoil. is where the minimum pressure occurs. Now we will be naming our parameters. So first we have the chord length C measured in meters. Take it as 1 meter. Next we have the velocity, which is 0.2 meters per second. And then of course the last parameter we care about is density, rho, measured in kilogram per meter cube. It's 1.2254 for air. Now we will start by calculating the force. So we'll be calculating the lift force and the drag force by going into line integration. First we'll start by calculating the force. And the drag force by going to line integration. We'll set all four boundaries. There is an expression for both lift and drag force. In this case, SPF dot T underscore stress for the x direction. Sorry, it's negative SPF dot T underscore stress. For the x direction. And it will be the same for the y direction. Obviously x represents the drag force and y represents the lift force. Drag and lift force. And now we are ready to evaluate. So here are the values, as you can see, for both drag force and lift. Now we want to show you how the drag force changes with the angle. We're going to take increments of 2.5. So we're going to show how each force changes with different angles. We will define a new parameters called alpha. minus 5 of course, which is the initial value. Here we will go back to the rotate section, change the angle to alpha, and then we will be performing a parametric sweep. So we will add, we're interested in alpha, and then we'll put a range of values from 0 to minus 20 degrees. With a step or an increment of minus 2.5. Now we'll be going to the stationary solver just so that we can reduce the tolerance because before it didn't really work. So we need to change the tolerance for it to compute. Now compute. This will take a while. Like a few seconds to a minute for it to show every value for different angles. I mean, it's showing us the convergence plot, so there must be working. And this is the iteration, of course, and the errors at the y-axis. And now it's almost done. So yeah, the study now is done. It shows the new velocity behavior with respect to minus 20 degrees actually, the maximum angle. So now we will check the force values. We will go to parametric solutions for dataset. We will evaluate. And it will show us the new lift force and drag force with respect to each angle. So as you can see here, from 0 to minus 0.5, it shows us different drag and lift forces that we actually got it on Excel, and we'll show it in the report. And of course we can also change the expression. We can use these parameters to calculate the drag coefficient and the lift coefficient by inputting the values C, V and rho using the formula we have always used in the course. Now one last thing is we wanna check the arrow surface for our airfoil. We'll just remove the surface because it's a bit blurry in this case. So now you can see the arrow profile on the around the airfoil. So yeah, thank you very much.